Today we're going to take a look at the sun. And if you're following along in OpenStax, the information is from chapters 15 and 16. Now, the name of our sun is Sol, which is where we get the word solar system from. Now, that name is more of a poetic name or a common name. It's not necessarily the astronomer's official name for it, but that's what its name is, or solar power. So what's the sun made of? The sun is made by mass about 75% hydrogen, about 25% helium. Now, it's really more like 73% hydrogen because everything else up to the element iron is only 2%. And the situation gets different if we look at the number of atoms. If you want to just look at number of atoms, it's 92% hydrogen, 7.8% helium, and then only 0.2% every other atom, carbon and oxygen and nitrogen and phosphorus, and even many of the elements that make up our bodies. Some even say an astronomer's periodic table would have two elements, would have hydrogen in one box, helium in another, and then just everything else below it. And in terms of the amount of atoms or the number of atoms in the universe, they're right. Most of the matter in the universe is going to be in the stars, not in the planets, because the planets are so much smaller. So most of the universe is hydrogen and helium. And this was first discovered by Cecilia Payne-Gaposchkin, which is interesting because she was the first woman in the United States to get a PhD in astronomy, and she just helped discover the composition of our sun. So it was a pretty important discovery. Another really interesting fact is that helium was first discovered in the sun before we found it on the Earth. In fact, it was named for Helios, who was a Greek sun god way back in the days of the Greek gods. And that's what helium means, the element found in the sun. And then a little bit while later, we did start to find helium. It's found in deposits above natural gas and oil. That's where they find it. Now, our sun is what's called a G-type star. And those refer to the color and how hot the star is. And just to give you some basic facts, it's about 150 million kilometers from Earth. For many of us, it would be easier to think of it as being, in terms of miles, 93 million miles if you're in the U.S. If you're not in the U.S. or you're more used to the metric, about 150 million kilometers. So even though we see it in the sky, it's really, really far away. In fact, it's so far, even my drawing the scale is not going to be right here. But when a photon of light leaves the sun, it takes 8 minutes until it reaches Earth. So in a way, we're seeing into the past. It's a sunny day right now, and I'm looking out, and the sun is hitting the tree that's outside my window. And that sunlight that I'm observing is 8 minutes old. Left its journey from the sun about 8 minutes ago. The sun is really heavy. It's about 333,000 Earth masses. So you could easily put all the planets of the solar system inside the sun, and you wouldn't be anywhere near close to the mass of the sun. You can't stand on the sun, but if you could, gravity would be about 28 times the pull of gravity that you and I feel right now. So it would probably squash us. The sun rotates the way we rotate in one day. The sun rotates in about a month, and actually varies. It's faster at the sun's equator and higher and slower in the upper and lower latitudes. You might wonder how that happens. The sun isn't a solid mass. It's not a solid rock, basically the way Earth is. So the gases and the bands of gases rotate at different rates. And we think it's about 4.6 billion years old. It's roughly halfway through its lifetime. But we'll talk about, well, how do stars end their lifetimes and how are they born later. Now, a really good question that was actually asked to me many years ago, and I'm sure I'm not the only person who was asked this, is the sun on fire? And how does it burn in space? Because we all know if you want to put out a fire on Earth, if you can starve it of oxygen, If you have a little piece of paper on fire, let's say on a lab desk, and you just put a beaker or a glass over it, it'll go out because there's no oxygen. Or we blow out a match. The CO2 in our breath doesn't burn. We've taken away the oxygen. So it's a question of, well, if the sun is on fire, how is it burning where there's no oxygen? It's not on fire the same way we have a campfire or a candle. It's actually a plasma. So there are 4 states of matter. We think about solid, and then we heat something up and we get a liquid, and then we heat it up some more and we get a gas. Well, if you could heat a gas, a superheated gas, you'd get a plasma. And you say, well, can we do that on Earth? Yes. Arc welding, which uses electricity and welding, they can get plasmas. You can get plasma from a lightning bolt. Lightning bolt will produce plasma. And what it is an ionized gas. Now, an ion is a charged atom or molecule. So what happens is the sun is so hot that the electrons are stripped from the atom. And I have a little picture down here. It's a hydrogen and helium plasma, which shows you what's going on in much of the sun. So the helium has lost some of its electrons, at least one of them. The hydrogen has totally lost of its electron. So you can see we have positive ions and bare electrons all floating around together in this plasma. So it's not an atom like we have in our body where the electrons are bound and they circle. It's not really a circle, but they orbit around the nucleus. Now, what's the source of heat? We've said so much of the universe is controlled by gravity. So in the sun is really massive. It's pulling and constantly for 4.6 billion years been trying to contract itself, trying to pull all the matter into the center. And this immense pressure, the atoms and the electrons are squeezed so close together that nuclear fusion occurs. Now, there's different layers to the sun. It's kind of like, the sun is almost, you could maybe like an onion. Let's start in the middle. So we have the core of the sun. The core of the sun is unbelievably hot, 15 million degrees Kelvin. You might say, well, what is that in Celsius? What is that in Fahrenheit? It's so close to 15 million, it's 15 million degrees. It almost doesn't matter the temperature scale at that point. That is the hottest part in the solar system. That's where we're getting our fusion. That's where the light is released. But what's really, really incredible is it takes 100,000 years for that photon to go from the core of the sun out to the edge. And then now once it leaves, 8 minutes to get to Earth. So it's incredible to say, well, why does it take 100,000 years? Well, the next zone out, and we can see in the picture, is called the radiative zone. The sun is very dense. If you can imagine you're at a big concert and you went to get a soda or get some drink for you and your friends. Well, you're at a big concert. Everybody's packed together like on a big baseball field or a big concert outside auditorium. Till you go and find your friends, you're going to be weaving in and out and maybe even bumping into the other people who are there. That's what happens with the light from the sun. The sun is so dense that these photons bump into the atoms, they get absorbed and re-emitted by some of the atoms, and they have to basically take them a long time to bounce their way out to the surface of the sun, and then eventually go and then shine out into the universe. Now the convection zone is this circular zone. That's where, and we have convection on Earth. We have convection currents in the ocean. We know that hot air rises. Well, the same thing is true for plasma. The hot plasma rises. It doesn't get cool by Earth standards, but still cooler than before, and it sinks. So there's this constant rolling there that we see kind of in the convection zone. And then the outer layers we'd call the photosphere or the chromosphere, the light sphere, and chromo means color. So that's where we're seeing the sun. And we can see that this convection is going on too, because when we look at the surface of the sun, it's not smooth. We see little areas of hotter areas and cooler areas, and we're seeing the mixing there. Now, a good question is, well, why is the sun yellow or, reddish orange? And it has to do with atoms. Atoms are quantized. So if we think about a regular old atom here, with its electron just going around, just pretend it's a hydrogen atom. The normal orbit or space for the electron is called the ground state. Now it absorbs energy, and there's a lot of heat energy involved here. And the electron jumps up to what we call an excited state. It now goes further and further away from the nucleus. If you could imagine spinning a yo-yo on its string, and then you want to give it a little more energy, let the string out a little bit. The electron will spin further and further out. But electrons don't like to stay in their excited state. They stay in their excited state fractions of a second. They have to get back down to the ground state. So if they absorbed energy on the way out, they have to release energy to go back down. Like if you throw a ball in the air, you give it potential energy at the top, and then when it returns to your hand, it has to emit or get rid of that energy, and it's a kinetic. In this case, the energy is emitted as a photon, which is a light particle. Now, why is it yellow and red? Why don't we see a green sun or a blue sun? It has to do with the fact that the atom is quantized. There's only certain orbits, only certain places where it can go. So it's kind of like steps. You can step on the first step going upstairs or the second step, but you can't stop at a 1.5 step. There's no spot there. Electrons are kind of like that. There's certain rings that they like to go to. They're not exactly rings, but they'll do for our model here. There's only certain quantized or quantities of energy that they can absorb, only certain spaces they can go to. That means on the way back down, there's only certain colors they can emit. So for example, for this atom, if it jumps up to this excited state and back down, it can only emit a red. Then here on the way back down, it only emits a green. And here it's going to emit a blue. Now you might say, well, why not kind of a green blue? I mean, we can make green blue with watercolor paints or something. It's forbidden. To make a blue green or a green blue, it would have to stop in the middle. And just like your stairs and my stairs in our house, there's no step there for it to go on. So the sun is red and or yellow and kind of orangish red because those are the places where there are steps for it to go to. And this is important because this tells us what kind of elements are there. You and I, and sometimes for certain jobs, you have to go get your fingerprints checked. And they run your fingerprints through the FBI database and make sure you didn't commit any crimes. We know there's hydrogen in the sun because, and we don't look at the sun directly, but if we aim a sensor at the sun and we look at the lights, we see a strong red line. We do see some other lines as well. We see kind of a light blue and a darker blue and a purple color. Every element has its own fingerprint. It's called an emission spectrum. So by seeing this red line, we know there's hydrogen in the sun. And helium gives off that yellow line. So, and yellow, and when you combine your yellow and your red, you get kind of an orangey color. So that's how we know that it's predominantly hydrogen and helium. And we know the relative brightnesses, that we have more hydrogen than we do helium. Now the corona, that's the very outermost edge of the sun, kind of right above the sun's surface. Now it's hot. It's about 1,000,000 degrees Kelvin. It's still cooler than the core, but still awfully darn hot. Now, when do we see the corona? We can see it during an eclipse. Again, not with our bare eyes. You have to use a filter. And not regular sunglasses. You have to get special glasses or special things to observe it. So the corona is visible when the moon blocks it out. It's a less dense gas. And surprisingly, in a way, we could even think about it extending past the Earth's orbit. Now, it cools down substantially as it moves away. You can see the rays get further and further spread out as the arrows go out. But the corona is really big. And a way to think about that corona extending past the Earth is something called the solar wind. What's the solar wind made out of? It's mostly protons and electrons. Nothing fancier, just regular old protons and electrons. So you can see the corona here, and you could see how it's extending. They come from the corona. Now, once you get out to the corona here, you're pretty far from the center of the planet. And we remember that gravity decreases inverse square. It decreases exponentially as you get further away from the center of mass. So once these protons and electrons get out here, I'll just call them P and E, they really can't be held by the gravity of the sun anymore. And so they get released out into space. Here's what's surprising. By releasing these protons and electrons out into space, the sun is losing 10 million tons of material a year. And that's incredible because you say, well, that's a lot of material. 10 million tons? I can't imagine 10 million tons. But it shows you how big the sun is, because the sun's been losing about 10 million tons of material a year for 4.6 billion years. And it's still there. It has not exhausted itself. You know, it would be like Bill Gates giving a few pennies a year away. He'll never miss it. Now, where did this solar wind come from? It comes from what are called corona holes. There's certain places where the sun's magnetic field is not concentrated. So if you look at the surface of the sun, there are certain spots because of the sun's magnetic field where it's not as concentrated and the particle can escape. Otherwise, the magnetic field from the sun would hold it in. Luckily, the Earth has a magnetic field too. We're very, very lucky the Earth has a magnetic field. So here's a surprising fact. If you have a compass, well, it'll point towards the north. We would say, well, that's the North Pole. But what we say the North Geographic Pole is actually a south magnetic pole. And it's kind of mind-bending. The north needle of your compass, the north end of the needle of the compass, wants to point towards the south. Be that as may, what we're really worried about is there's this fundamental fact in physics, and there's even a law that has to do with it called one of Maxwell's laws. It's that charged particles interact with magnetic fields. We know this. Neutral particles don't. So these protons positive and electrons negative will interact with the Earth's magnetic field, and they get funneled, luckily, away from the habitable zones. They get funneled away from Pennsylvania and Britain and China and the Middle East and Africa and Australia and Asia and all that. They get funneled to the north and the south. And in the north, and the south, they start to interact with our atmosphere. And that's what we call the northern lights, the aurora borealis. So they're very pretty, but they're actually charged particles hitting our atmosphere. And the question is, well, is it dangerous to look at them? Probably not, because they're getting absorbed in the process of coming down into the atmosphere. And you can see them in the south. That's called the aurora australis. Without the magnetic field, we would be in huge trouble. The solar wind, all those protons and electrons hitting our atmosphere for billions of years would strip our atmosphere, would take our atmosphere out into space. Kind of like the way if you had a little bit of sand or dust on a porch, you could blow on it, and or if you had a leaf blower, you could blow the dust away. You'd be blowing the atmosphere away of our Earth. The sun partially stripped Mars. That's one of the reasons Mars has a fairly weak magnetic field, and it just hasn't been able to hold on to much of its atmosphere. You may have heard of sunspots. These are actually cooler areas of the sun. Now, cooler is a relative term. Those cool areas of the sun are still 3,800 Kelvin versus normally about 5,800 Kelvin. Now, as we said, it's caused because the sun actually has a magnetic cycle, a sunspot cycle. The magnetic field varies. So why they're important, and again, we don't want to look at them with our bare eyes, but why they're important is with the right type of telescope, we can look at them and we can see, oh, the sun's not rotating at the same speed, or the atmosphere isn't rotating at the same speed. It's fastest at the equator and less at the upper and lower latitudes. And it's related to the solar cycle, and it should be said that the energy output that reaches the Earth, the change is only like 0.1%. So during a sunspot cycle, it's not that it's going to be radically cooling or heating the Earth. So what's the sun's job? Just like we all have jobs, or we hope to get jobs, the sun's had a job too. And its job is related to the most famous equation in science, E = mc squared. Now what does that mean? E is energy, m is mass, and c is the speed of light squared. Now, the speed of light never changes. So that's really for us going to just be a factor. What it shows us is, and it's a really, really big number, is if you have a little bit of mass, you can convert it to energy. Matter and energy are not really separate things. Matter can be converted into energy. Now, what kind of energy? Because it's just to say energy is a very vague term. One type of energy is kinetic energy. It'll cause the atoms and particles to move faster. And the other type of energy that we're really interested in is light energy. And light energy is carried by the light particle, the photon. There's two possible things that nuclei can do. They can do fusion, which is where they combine. So if we look at the picture down here, we're taking two particles and they're getting fused. When you fuse two ideas, you bring two ideas together. The nuclei combine. As far as we know, it only occurs naturally in stars because you need a very, very hot temperature. We can do fusion in the lab. However, there's a really big one in San Diego I was fortunate enough to see one time. However, it takes a lot of energy to do this. So the problem is, well, the sun gives out all this energy. Why can't we just use this in a lab and get all this energy and, make electricity out of it? Right now, we have to put so much energy in that we don't get enough out for it to be practical. It would be like putting 10 gallons of gasoline in our car, and only getting $10 of gasoline in the car and only getting $5 worth of motion. It wouldn't be worth it. Now, will that change? Possibly, and there's a lot of hope for fusion. Fission is when things split. They fizz apart. This occurs naturally through radioactivity. And we've harnessed it with nuclear power and, unfortunately, nuclear weapons. So, on Earth, we use fission, both for peaceful and warlike things, but we use fission. We can do fusion, but we haven't found a way to do it practically yet. And I remember reading about fusion as a possible power source back when I was in high school many, many years ago. So the sun's main job, and we're going to go through the 3 steps, but then we'll simplify it. The sun's main job involves 3 steps. The first is to make hydrogen-2, which is called deuterium. So we take one hydrogen atom and another hydrogen atom, and the blue is the proton. Well, one of the protons gets converted into a neutron. It's still hydrogen because it has only one proton. And there's a couple of byproducts. The neutrino, which is a little energetic particle, and a positron, which is a positive electron. And you won't have to memorize all these steps. Don't worry about that. But just keep the neutrino in mind. That's going to be important when we talk about exploding stars later on. Now, it's got a slightly heavier particle. It's almost like taking two Legos and putting them together, although the one Lego has changed a little bit. And it can find another hydrogen, just a plain old hydrogen, and we can make helium. A byproduct there is the gamma ray, and that's going to be important. So we got neutrinos and gamma rays as important byproducts. And then we could take two of those helium-3s and make helium-4. Helium-4 is the more common, stable form of helium, and you actually get a couple extra hydrogens released in the process. So as I said, we're going to simplify this a little bit in the next slide. Let's just look at the overall equation. I have the more fancy equations down there. So for those of you who had maybe a really strong chemistry or physics course in high school, you might be interested in those. I'm not going to focus on them right now. I want to just look at this part up here. Basically, overall, and it takes 3 steps to do it. We don't care about the steps so much. Is it takes 4 hydrogens, 4 hydrogen atoms, and converts them into helium. The byproducts are the gamma rays, which are light. And what's the sun's main job? To give off light. And you get a couple other byproducts, positrons and neutrinos, that we're going to deal with, as I said, in the next video. So think about if you had a bag of Legos and you took four of them together and make helium, 4 individual Legos and make helium, 4 more individual elements and make helium. Eventually, you're going to run out of the individual Legos. You don't have any more or less than you started, but now you've got a whole bunch of them stuck together as helium, and you don't really have much hydrogen left. So later in a star's life, once it starts to run out of the hydrogen, it can then start to make some heavier elements, heavier than helium. But it doesn't want to do that. That takes more energy, so it doesn't do it until it runs out of the hydrogen. Now the gamma ray photon. We said it takes 100,000, these are estimates, some might even say up to 1 million years. It takes an incredibly long time to get from the core out to the edge of the sun. So we're talking greater than 100,000 years. And then once it's here, 8 minutes to get to Earth. And it has nothing to do with the speed of light. Nothing to do with the speed of light. The speed of light is constant here. The problem is, kind of like you trying to get through that crowd at the concert, each of these gamma ray photons only travel about a centimeter, at most about a centimeter, before they hit another atom. So you can see that. It gets emitted and then hits another atom. Now that excites that atom, and then eventually it'll get re-emitted again. The thing is, there's no preferential direction for it to get re-emitted. In fact, it could even bounce back towards the core, which would totally defeat the purpose of trying to get to the surface. It doesn't know. It just does what it does. So all this absorption and re-emission, it takes a long time for it to bounce its way out towards the surface. We see the sun. We see visible light. Gamma rays are invisible. We cannot see them. We could detect them if we had a detector, but they are not visible to our eyes. So what happens is as it's in this process of bouncing and getting absorbed and emitted, some of the energy can be emitted in the visible range. So on its long, long journey on the way out, it can go from gamma, which is very high energy, we cannot see it, eventually it can work its way down to red and yellow light and colors that we are able to see in the visible range. The sun is stable, and it's what's called hydrostatic equilibrium. Now, by the term hydrostatic, you might think it has something to do with water. It doesn't. There's 2 forces fighting in the star constantly. One is gravity. Gravity wants to compress the star. However, it's really hot in there. Those particles are moving around and moving around and moving around, and they're creating pressure. Like when you blow up a balloon, The atoms in a balloon are moving and moving and bouncing against the side of the balloon, and that's what's creating the pressure. So this pressure is caused by the moving particles, and they move because there's fusion going on. So it's really nice that the gravity and the pressure of our star balances. They're equal so that the sun doesn't swell out or shrink down. Now, does that ever happen? Yes. Later on in a star's lifetime. That's the death of stars. Once the nuclear fuel runs out, again, using the Lego analogy, once you've taken all your little hydrogen Legos and fused them into helium, and then maybe you took all your little helium Legos and fused them into a heavier atom, at a certain point, you're not getting as much energy. The star is cooling down, you have less pressure, less heat, and the star will collapse.